This is a video on Rolle's theorem and the mean value theorem, which is in section 3.2. We're going to start with Rolle's theorem, and before I introduce the theorem, we're going to start with an activity so you can kind of figure out what it means for yourself. So if you want to pause the video and try this activity, what you're going to do is place 2 points on the coordinate plane below that have the same y value. So that gotta have the same y value. Connect the points with a continuous function, so there can't be any holes or asymptotes or jump discontinuities, and a function that's also differentiable, so you can't have any sharp turns or cusps or discontinuities. So go ahead and do that now. Pause and just draw a function on this xy plane. And then I'm going to get started. Alright, so I need the function to have the same y values. Alright, so I make them have the same y values. Function has to be continuous and differentiable. So I don't see any sharp turns. It's continuous and differentiable. So now when I look at this graph, I see that there's at least one place where I have a horizontal tangent line where the slope changes from positive to negative, or over here negative to positive. So a conclusion that I can make now by looking at my graph is there must exist at least one point on your function where you can draw a tangent line that is horizontal. All right. Or what that means is where the derivative equals 0. So check that on your function. The way I drew mine, it happened to be that I had two. I had one right here and one right here. Just check it on yours and see if you got the same thing on yours. So this idea basically illustrates Rolle's theorem. So let f be continuous on the closed interval. So it's got to be continuous. That's what we did up here. And differentiable on the open interval. You got to be able to take the derivative. So no sharp turns, no discontinuities. On the open interval AB. If f of A equals f of B, that's saying the endpoints have an equal y value. Endpoints have an equal y value. Then there's at least one number C such that f prime of C is 0. So you're going to have at least one horizontal tangent line. So I'm going to go through and number this. We're going to call this condition 1. It's got to be continuous. 2 is going to be that it's differentiable. So we got to check these two things first. The third thing we got to check is, are the y values at the endpoints equal? And if all three of these are true, we know for sure there's going to be at least one place where there's a horizontal tangent line or where the derivative equals 0. So 1, 2, 3, and then we can actually find the value where it equals 0. So go ahead and finish writing this down, and then I'm going to do an example on this. It's pretty straightforward. We're just going to kind of run through the steps and then find C. All right, so determine if Rolle's theorem applies to f of x equals x to the fourth minus 2x squared on the interval -2 to 2. State thoroughly the reasons why or why not the theorem applies. If the theorem does apply, find the value of C guaranteed by the theorem. So this means I got to check three things: continuity, differentiability, and the y values of the endpoints. So it says state thoroughly the reasons. We're going to start there. All right. Reason number 1. I see that this is a polynomial function. There are no x's in the denominator. We don't have any discontinuities. So I can say f of x is continuous on -2, 2. It'd be a different story if we had x in the denominator or something similar, but this function is always continuous. All right. There's no way to find a discontinuity here. So we met condition 1. We can kind of check that off. If you review back to the theorem, condition 2 is that this function is differentiable. I can take the derivative of this function. All right. There's no sharp turns here. It's not an absolute value function. This function is differentiable. We've been taking the derivatives of polynomials for a while. So f of x is differentiable on -2, 2. So we got our second condition. All right, third condition, I have to check that. So I'm on 3. The y values at the endpoints are equal. So what we do for that is I take my x values of the endpoints and I plug them in to see if I get equal y values. So I'm going to take f of -2, plug it in. That gives me -2 to the 4th minus 2 times -2 squared. I get positive 16 minus 8, which is 8. Let's check the y value of the other endpoint. I get 16 minus 8 again, which is 8. So I showed that the y values at the endpoints are equal. So f of -2 equals f of 2, which is equal to 8. So I met that third condition. We can check that off. So now this definitely means now Rolle's theorem applies. All right. So we kind of answered the first question, determine if Rolle's theorem applies. That's a loaded question. That means you got to check these 3 things. Now, state thoroughly the reasons. We did that right now. We said it was continuous differentiable and we showed the y values were equal. Now, if it does apply, find the value of c guaranteed by the theorem. So now we're on the last part. It says that f prime of c has to equal 0. So I got to find where exactly this horizontal tangent is. So now for this last part, I'm going to take my function, which was f of x equals x to the 4th minus 2x squared. I got to take the derivative, which is going to be 4x cubed minus 4x. I have to find out when this equals 0, find my critical value, factor out a 4x, and I'm left with x squared minus 1 equals 0. We could keep factoring. All right, so my critical values are x equals 0, 1, and -1. So these are the values of c that if I plug them into the derivative, I'm going to get a derivative that equals 0. So this is the last part. If the theorem applies, find the values of c guaranteed by the theorem. That's this right here. All right. So this concludes Rolle's theorem. So if I were to graph this function, my endpoints would be at 8, and I would have horizontal tangent lines at these x values. All right. So now that pretty much concludes Rolle's theorem, and we are on to the mean value theorem. All right. This shows up on the free response section quite a bit for the AP test. So we'll be working a lot with the mean value theorem. All right. If f of f is continuous on a closed interval AB and differentiable on an open interval AB. So we're starting with the same criteria as before. When we use the MVT, or mean value theorem, abbreviated MVT, we always have to check that it's continuous and differentiable. So if a function is continuous on a closed interval AB and differentiable on an open interval AB, there's got to be a number C in AB such that f prime of C equals f of B minus f of A over B minus A. Now, all this is saying is there has to be a point where the instantaneous rate of change I'm going to abbreviate rate of change equals the average rate of change. This is the formula for average rate of change, just like from algebra 1, 2, and pre-calc, y2 minus y1 over x2 minus x1. And then this is the derivative, the instantaneous rate of change. So if a function's continuous on a closed interval, differentiable on that open interval, there has to be a number c such that the derivative equals the average rate of change. Now, I need to give you a visual on this so it makes more sense. All right, so here's a function that's continuous on the interval AB. There's no holes, asymptotes, or sharp turns. And it's continuous. All right, continuous means there's no holes, asymptotes, or jump discontinuities. It's differentiable because there's no sharp turns or cusps and discontinuities. So it's continuous and differentiable. So all the mean value theorem is saying is if I find the slope of the secant line, so I'm going to start with this side of the equation. The slope of the secant line through the endpoints of the interval would be the slope of this line right here. All right, so this is the slope of this line is f of b minus f of a over b minus a. I'm looking at the slope of this line. Because the function is continuous and differentiable, there has to be a point on the curve where the slope at that point is the same as the slope of the secant line. So at this point right here, all right, I can draw in my tangent line. So at this point where x equals c, and I can see that the slope of the secant line equals the slope of the tangent line. So that mean value theorem says that if a function is continuous and differentiable on an interval, there's at least one place where the slope of the tangent line at a point equals the slope of the secant line through the endpoints. All right, slope of the tangent line at a point equals the slope of the secant line. Slope of the tangent line equals the slope of the secant line. There's got to be one place. So pretty much the MVT can be used to show two things. That there's a tangent line that's parallel to the secant line through the endpoints, kind of like I showed up here, a tangent line that's parallel to the secant line. And it shows there's a point where the instantaneous rate of change equals the average rate of change. All right, shows two things, and this is your visual. You can always go back to this visual. So now, let's do an example with this. All right, determine if the MVT, mean value theorem, applies to f of x equals 3 minus 5 over x on the interval 1, 5. State thoroughly the reasons why or why not the theorem applies. If the theorem does apply, find the value of c guaranteed by the theorem. All right, so first thing we got to do is figure out if it meets the criteria of the mean value theorem. This goes for all MVT problems. Is f continuous on the interval? Is it differentiable? All right, so let's look at this function, f of x equals 3 minus 5 over x. The only discontinuity here is when x equals 0, because you can't have 0 in the denominator. However, 0 is not between 1 and 5. So f of x is continuous on 1, 5. I can plug every single number between 1 and 5 in for x, and the function will be defined, because 0 is not between 1 and 5. Now, if it said negative 1 to 5, it wouldn't be continuous, but 0 is not between 1 and 5. All right, so I got the first criteria. Second piece of criteria. Is f of x differentiable? Yeah, if I look at this, I can take the derivative here. There's not going to be any sharp turns, cusps, or discontinuities between 1 and 5. Yeah, there's a discontinuity at 0, but 0 is not between 1 and 5, so f of x is differentiable on 1, 5. All right, so it's differentiable between 1 and 5. All right, now this means that if I look back at the mean value theorem, we showed it's continuous and differentiable, so yes, the mean value theorem applies. All right, so we got the mean value theorem applies, and we thoroughly stated the reasons. If the theorem does apply, find the value of C guaranteed by the theorem. So our theorem is saying, the MVT says that f prime of C has to equal f of B minus f of A over B minus A. So, or I'm saying the instantaneous rate of change equals the average rate of change, or the slope of this tangent line equals the slope of the secant line. So we're saying the slope of the tangent line equals the slope of secant line. All right, so what I can do now to find this value is, let's first start by finding the slope of the tangent line. So I know f of x equals 3 minus 5 over x. To find the slope of the tangent line, that's the instantaneous rate of change, I just take the derivative. All right, so now what I do is the derivative of 3 is 0. Right here for this negative 5, I bring the x up. I have x to the negative first power. I'm going to take the derivative of this. I'm just doing some side work. And I get 5x to the negative second, which is 5 over x squared. So my derivative is 5 over x squared. All right. So I'm saying this derivative at some point has to be equal to the slope of the secant line. So now we can actually find the slope of the secant line. My interval is 1, 5. This is A, this is B. So I'm going to find f of 5 minus f of 1 over 5 minus 1. That's the slope of the secant line, the slope of the line through the endpoints. So f of 5 is going to be 3 minus 5 over 5, which is 2. F of 1 is going to be equal to 3 minus 5 over 1, which is negative 2. So now I can just plug in my values. I'm going to have f of 5 is 2 minus f of 1 is negative 2 all over 5 minus 1 gives me 4 over 4, which is 1. So the slope of my secant line is 1. The secant line through the endpoints. So now the mean value theorem is saying that the instantaneous rate of change, the slope of the tangent line, has to equal the slope of the secant line. So I can take these and set them equal. So 5 over x squared equals 1. Let's solve for x. Multiply both sides by x squared. I get 5 equals x squared. Take the square root, and x equals plus or minus the square root of 5. Now, this gets just a little trickier. So that means x is positive square root of 5 or negative square root of 5. However, the interval I'm talking about is between 1 and 5. Negative square root of 5 is not in this interval. So my only answer is x equals the square root of 5. So let's review. First thing for the MVT, show it's continuous and differentiable. That means the slope of the tangent line, or the derivative, equals the slope of the secant line. You find the slope through the endpoints. From there, you set the derivative equal to the slope of the secant line and solve, making sure your x value is in the original interval. All right, let's do another MVT problem. All right, find an equation of the tangent line to f of x equals 2x plus sine x plus 1 on 0 to pi at the point which is the solution to the MVT, meaning that I'm finding the point where the tangent line, the slope of the tangent line equals the slope of the secant line. So same thing goes though, just like before, I got to show the MVT applies. So for step 1, all right, let's check if it's continuous. I see no terms in the denominator, no asymptotes. This function will be continuous. So f of x equals 2x plus sine x plus 1 is continuous on 0 to pi. All right, there's our first criteria to check if the MVT applies. Number 2, is it differentiable? Well, we're not going to have any sharp turns, asymptotes, or cusps because there's nothing in the denominator here and no absolute values. So f of x is differentiable on 0 pi. So the MVT applies. All right. Now, let's do the same thing. I got to show where the slope of the tangent line equals the slope of the secant line. All right. Well, let's first start by finding the derivative. So f prime of x is going to equal, if I look up here, I'm going to get 2 plus cosine x. All right. So there's my slope of the tangent line, just like I wrote it over here. I just didn't feel like writing it again, the slope of the tangent line. So now let's find the slope of the secant line. Our interval is 0 to pi. So I'm going to have f of pi minus f of 0 over pi minus 0. Now, f of x was equal to 2x plus sine x plus 1. So f of pi is going to equal 2 pi plus sine pi plus 1. Now, if I think about the unit circle, all right, at pi, that's negative 1, 0. The y value is 0, so the sine of 0, the y value is 0. So I'm just going to end up with 2 pi plus 0 plus 1, which is 2 pi plus 1. Now let's find out f of 0. I'm going to get 2 times 0 plus the sine of 0 plus 1. If I think about the unit circle again, at 0 radians, the coordinate is 1, 0, and the y value is 0, so the sine of 0 is 0. So I'm just going to have that this equals 1. Now what I need to do is find the slope. So actually, I'll just do it up here. So f of pi was 2 pi plus 1 minus 1 over pi. That gives me 2 pi over pi, which is 2. So the slope of my secant line is 2. So now I need to know where the slope of the secant line equals the slope of the tangent line. So I'm going to say f prime of x, that was this, has to equal 2. Or you set the derivative equal to the slope of the secant line. So 2 plus cosine of x equals 2. Subtract 2 from both sides. I'm looking for where the cosine of x equals 0. Let's draw a unit circle. This is 1, 0, 0, 1, negative 1, 0, 0, negative 1. The interval I'm talking about is from 0 to pi, because that's what's in the original problem. There's only one place from 0 to pi where there's an angle where the cosine is 0, and that angle right here is pi over 2. I don't have to worry about this one down here because I'm only talking about the interval from 0 to pi, not 0 to 2 pi. So x equals pi over 2. Now, the last part is I didn't answer the question yet. I found the point, or the x value, where the mean value theorem applies, where the slope of the tangent equals the slope of the secant. But I wanted the equation of a tangent line. So we have to throw this back a little bit. My next goal is to find y minus y1 equals m times x minus x1. I know my x value is pi over 2. All right. My original function is f of x equals 2x plus sine x plus 1. So now I need to, and then my derivative was 2 plus cosine of x. So I'm going to use my derivative to find my slope, my f of x to find my point. So let's find f of pi over 2. I'm going to have 2 times pi over 2 plus sine of pi over 2 plus 1. That's going to give me pi plus sine of pi over 2 plus 1. Let's analyze the sine of pi over 2 real quick. All right, I know that this is pi over 2, and this point right here is 0, 1. The sine is the y value, so I'm going to have pi plus 1, or pi plus 2. So my point that I'm going to use my x1, y1 is going to be pi over 2 and pi plus 2. All right, so I got my point is this. I can label this as point if you want to. All right, now let's find my slope. All right, so I'm going to find f prime of pi over 2. That's going to be 2 plus cosine pi over 2. I'm going to look at the same unit circle. Here's pi over 2. The cosine is the x value, 0. So I'm going to have 2 plus 0, or 2. So my slope is 2. So I'm going to use this and this to write my equation. So I'm going to have y minus y1 is pi plus 2, put in parentheses, pi plus 2, equals m, which is 2, times x minus pi over 2. All right, so to summarize this problem, first thing I did was show that MVT applies by showing it's continuous and differentiable. You want to write out steps. From there, I had to find where the derivative, the slope of the tangent line, equals the slope of the secant line, and I went through and found the slope using f of b minus f of a over b minus a. From there, I set my derivative equal to the slope I found, and I solved. Now, to get my tangent line, this is the x value I used. So I came over here. I know I'm going to have a line in point-slope form. First, I plugged in pi over 2 to find my y value in the original, plugged in pi over 2 to find my slope. Wrote the equation of my tangent line. All right, and last. All right, sometimes the MVT does not apply. We're just going to run through this real quick, and then this is the last part. When the MVT doesn't apply. So there's two conditions. One, a function has to be continuous on an interval. Two, it's got to be differentiable. So we got to check that for these functions. Explain why we cannot apply the MVT to the functions below on the given intervals. So looking at A, f of x equals 3x minus the absolute value of the quantity x minus 3. All right, I know this function is continuous. I can plug in any x value. However, because there's absolute value, there's going to be a sharp turn or a corner, So that corner happens when what's inside the absolute value equals 0. So I know that this is not differentiable. F of x is not differentiable at x equals 3. So the MVT does not apply. And 3 is in our interval here. So that for sure does not apply. All right, let's check here. All right, g of x equals 2 over x plus 2. Well, I could take the derivative of this. I could either use the quotient rule or bring up the x plus 2 and apply the power rule. So it's differentiable. However, it's discontinuous at -2 because -2 plus 2 gives you 0 in the denominator. And -2 is between -3 and 1. So f of x is discontinuous at x equals -2 because it's discontinuous. So the MVT doesn't apply. There's only two things that got to happen. It's got to be continuous and differentiable. If one of them doesn't apply, the MVT doesn't apply. Last, let's check this. H of x equals x to the 2/3. Well, I could plug in any x value here. That's not going to matter. We can take the derivative. Let's do that. I get 2/3 x to the -1/3, which is 2 over 3 times the cube root of x. Now, if I look, this function is not differentiable. The derivative doesn't exist when x equals 0. That would give us, thinking back to our last unit, a vertical tangent line because I would have 0 in the denominator. 0 in the denominator, vertical tangent line. So h prime of x doesn't exist at x equals 0, and x equals 0 is in our interval, so h of x is not differentiable at x equals 0. All right, so the MVT doesn't apply. All right, this concludes the video on Rolle's theorem and the MVT.